So first of all, I want to thank organizers for inviting me to this. Yeah, even closer. Okay, who invited me to this wonderful meeting? And what I would like to do first, I will apologize for experts in this field, which is actually developing pretty actively these days, because the audience is pretty broad, and what I will tell might be for experts not contain too much of new stuff. But my goal is to make everything clear and as simple as it actually is. So what I want to start with is celebrated phenomena which was discovered more than 60 years ago by Phil Anderson. And this is phenomena of that is known as Anderson localization. And this is about properties of eigenstates of a Schrödinger equation in a random potential, which on this picture is represented by some impurity centers in a crystal. And at the beginning, people didn't believe, and now we consider it still as one of the interesting and inspiring ideas. So basically, it means that if we consider this problem, then there are two possibilities. One, which can be realized when dimension of your system is bigger than 2, so 3 in our world or higher. And it means that the wave function, although random, will be a wave function of a particular eigenstate, will be present everywhere. Somewhere amplitude will be less, somewhere bigger, but everywhere. In contrast with localized states, where the envelope of the wave function or density profile will be decaying from a certain random place in the crystal exponentially, and the corresponding characteristic length is known as localization length. And later it was understood that at low dimensions, namely 1 and 2, all states are localized, and this extended situation is not doesn't exist. And since then, there was a lot of experiments. So originally, Anderson proposed this idea to describe transport of charge and of spin in solids, but situation with this is a little bit more complicated, as we will see. But people observed phenomena of localization in for other systems, like localization of microwave. If you add disorder to some microwave cavity and study the distribution of intensity of electric field, you can get depending, for example, on frequency of your microwave, either something localized or something more or less broadly spread in the cavity. Localization of light, I just cited several papers, especially the last one I find extremely beautiful demonstration, and ultrasound. So a whole lot of classical waves were shown to be localized according to Anderson, and even material particles were also shown to get localized in experiments with cold atoms. Now, from this introduction, let me go to the model which Anderson introduced. And this model will be useful for us when we will generalize this story. Namely, the model consists of, Hamiltonian consists of two parts. One is diagonal part with some random on-site energies, I numbers the sides of this lattice, and second allows hopping from one side to another, second part of the Hamiltonian, and I just forgot somehow to write this IIJ in front of this, which is the probability of hopping. And for Anderson model, it was assumed to be 1 for nearest neighbors and 0 otherwise. And if I would know what Steve Strogach will speak about, I will probably construct my talk in slightly different way. But what I want to emphasize is that this second term basically can be written in terms of some spin 1/2 operators, where spin up corresponds to occupied states and spin down corresponds to empty state. And this this term is basically a product of S plus S minus, which is nothing but XY model. So this tight binding model is nothing but XY model for spin 1/2. And what Steve was speaking was XY model for spin classical, which is equal to tends to infinity in quantum units. And what Anderson considered was going beyond to this, instead of this epsilon I, Steve wrote omega I, but this is the same story. So if you will put all of epsilon I equal to each other, you will get, of course, for a crystal, usual tight binding model, and all states being Bloch waves and everything that we learned in the introductory course of solid state physics. And the statement, so Anderson actually made this problem much more interesting by assuming that epsilon i's are random and independent from each other and uniformly distributed in this interval from minus W to W. And demonstrated, I don't have time to repeat his demonstration in a very kind of convincing and deep way. He demonstrated that if disorder is exceeds certain critical value, then all eigenstates are localized, and localization length is finite. And from the point of view of charge transport, we would deal with insulator. And for W smaller than the critical value, we expect all states to be extended. And from electric point of view, we will deal with the metal. And as I already mentioned, there are situations like 1- and 2-dimensional crystals where WC equals 0, and arbitrary disorder actually leads to the localization. Now, in order to get some intuition, let me consider the simplest form of the Anderson model, namely two-well potential, where we have two sites, two on-site energies, and some matrix element of the transition between them. And then we all know that there are two possibilities. One is off resonance possibility, when difference between the diagonal matrix elements of the Hamiltonian is large as compared with the tunneling matrix element. And then states, there are two states, and both of them are very close to the on-site states. And corrections are small. And second possibility is opposite inequality, when this difference is small as compared with the matrix element. And then we're dealing with bonding and anti-bonding state sum or difference of two on-site states. And this is called resonance limit. And what you can see is that if in the first off-resonance case your particle is either on one side or in the other side, in the second state, probability to find it in each side is equal or more or less equal and close to 1/2. And then making a step from two-well potential to Anderson model, we can speculate that for weak disorder, we will get these resonances only rather few of them. They will be far from each other and will not change too much the eigenstates which are on site or close to on site. And when we will keep decreasing disorder, matrix elements will start to prevail. We will get many resonances. They will overlap, and in the end of the day, we will get extended states. Now, a little bit about the transport in disordered systems, let's say in doped semiconductor. So if you have low level of doping so that all your eigenstates are localized, then there is no transport. You basically put all of your electrons on certain sites, field them, and there is no way to make a transition from one side to another because you need to compensate for the energy difference between occupied and non-occupied state, and there is nowhere way where you can get it. So at zero temperature, if your states are localized, then conductivity is equal to 0. But there is a way to get finite conductivity if you are considering some other subsystem in your system, namely phonons. And the story that I mentioned here is known as phonon assisted hopping, where we wait for a phonon with energy h omega exactly equal to the energy deficit that we need to make a transition from state alpha to state beta. And as it was shown by Mott many years ago, what you will get this strange stretch exponent behavior of the temperature dependence of the conductivity, which is universal. It doesn't contain anything about phonons themselves, only about localized states, and there will be this prefactor, which is usually power-like, which is mechanism dependent. And why I'm speaking about mechanism is that nature of phonons here is not important. What is important is that these excitations are actually excitations with continuous spectrum, and this continuous spectrum goes down to 0 frequency. Now, the question that people started to worry some time ago, and even before this paper of Fleischmann and Anderson in 1980, is the following: that if we are so happy with phonons, we know that finite conductivity means that there is some electric Nyquist-Johnson noise inside your crystal. Why this type of the hopping conductivity cannot take place without phonons, just due to existence of electric noise of real electron-hole pairs in your system. And the basis for this was that indeed the same third Neville mode showed that there is AC conductivity, which is finite, and then there is fluctuation dissipation theorem that tells that the conductivity, AC conductivity means noise, and why not this noise to make hopping conductivity? And the reason is the following. Just to understand the origin of the whole problem, is that this noise comes from some transitions between the localized states, and in order to get the energy conservation, you need to find exactly two pairs which are exactly in the resonance, and this exactly means that normally they will be infinitely far from each other, and because they're infinitely far, then the matrix element will vanish, and as a result, this non-universal prefactor will also vanish. And this made the Anderson and Fleischmann to conclude that interaction between electrons will not destroy localization, which in fact was kind of impossible, because what we know from another side of the story, from so-called weak localization, is that if localization length exceeds some length at which phase coherence is destroyed, then we should have normal classical metallic behavior, and it should mean that at certain finite high enough temperature, we should have finite conductivity without phonons, even if the zero temperature states are localized. And the story is that actually what happens is that there is a kind of intermediate answer, which means that there is certain critical temperature below which conductivity is exactly zero. So whole system, taken into account interaction between your quantum particles, is localized. And at high temperatures, you have finite conductivity, which we will call metallic behavior. And this is still quite unusual metallic behavior because very strong temperature dependence. So these are the papers where we were describing this story. Again, I don't want to go into details of the calculations. And as I told, this phenomena is called many-body localization, which means that many-body wave functions, not one particle wave function, but many-body wave functions are localized in certain functional space. Now, just very quickly again, some intuition and some kind of physical picture. So what happens, what is the physics? And the physics is the following, that in a theory like Mott's theory of phonon assistant hopping, it was assumed that one phonon comes and generates one hop of electron. And this is correct if we forget that electrons can interact with each other, but if not, one phonon can cause more than one transition in electronic system. They can perform many hops, and you can speak about cascade that is caused by phonon, and we can speak about size of the cascade, how many hops was generated, and the higher the temperature, the more of these hops will be generated, and at certain critical temperature, this number will diverge, and then you understand that you don't need this original phonon because system will be extended even without phonons. So this is the physics, and now a little bit of theory. So I have to mention that localization beyond Anderson picture and through one particle propagation in disordered media was started with this paper of Shmuel Fishman, Grempel, and Rick Prange in '82, who studied the kicked rotor rotator problem and found that in quantum regime you have some analog to the Anderson problem, and in contrast with classical situation when this kicked rotor keeps increasing its energy to infinity, quantum one is localized, and angular momentum is not going to infinity. And what is important is that this system is not disordered, and still we have localization in the angular momentum space. And in general, sorry for these marks, I don't know where it's from. So what I want to start discussing now is a general quantum problem when Hamiltonian consists of two parts. One part is integrable, and another violates this integrability. And just to remind, classical integrable system is the system where you can separate variables. If you have d degrees of freedom, you have d integrals of motion, and because of this, all the trajectories are confined to tori's, which have dimension d, in contrast with the energy shell, which dimension is 2d minus 1. And as soon as d is bigger than 1, the tori dimension is lower than energy shell dimension, and it means that system is not ergodic because it's not spread all over the energy shell. And then we know that if we will violate integrability gently, at the beginning we will get some kind of interesting but complicated phenomena, which means that system behaves almost as integrable. Then there is huge intermediate regime where system still does not believe as the typical system that considered is in statistical physics, which obeys all the equipartition postulates and all these properties that we learn from Boltzmann and Gibbs. And only when we completely destroy an integrability, then we will get something like that. Now, again, I want to remind you that there is this celebrated Kolmogorov-Arnold-Moser theory and theorem that claims that if perturbation is arbitrarily weak and smooth, then we have almost all of the tori may be deformed, but still exists, and ergodicity doesn't take place. Now, what I want to do is to speculate now on what can happen in the quantum situation. And what I will do, I will consider first the classical problem with d much bigger than 1 degrees of freedom. And I want to consider it in the space of the integrals of motion. Remember, we have d integrals of motion. And then if system is integrable in this space, our system, our tori is a point. Each point in this space corresponds to the tori. And what the Kamm theorem tells is that probably for most of the original conditions, even after we violate integrability, of course, this point will start to move, but it will not go too far, and this motion will be confined to small region in the energy shell, or close to the energy shell. Now, what will happen in the quantum regime? In quantum regime, we also can consider everything in space of quantum numbers, but these quantum numbers, not integrals of motion, they are called quantum numbers because normally they are quantized. For example, the simplest integrable model, so-called rectangular billiard, we have two integrals of motion, which is horizontal and vertical components of the momentum, and energy shell is, of course, determined by this equation, px squared plus py squared, so it's a circle. And we know that as soon as we quantize this system, we will get quantization of this momentum, and instead of the continuous space of quantum numbers, we will get the something that looks like a rectangular lattice. And this is, in fact, generic for a whole class of the systems that we indeed can speak about the discrete points, which each corresponds to a quantum state of the integrable Hamiltonian. And this perturbation will lead to connections between the sides. So it will create some bonds for this lattice, which actually, before this perturbation, you cannot even tell which sides are close and which are far from each other. And then, by analogy with the classical result, we can suggest that indeed, even in the presence of the non-integrable perturbation, we will get eigenstates of your system, of our system, which is which are not fully spread all over the energy shell, but rather will be localized close to the energy shell by, let's say, few sides of the original lattice. And I hope you already see that we have some generalization of the Anderson model because we have a lattice, we have matrix elements of the transitions, and if matrix elements are kind of, in a sense, connecting states that are in some sense close to each other, or some small number of sides, then you will have Anderson model. And of course, the diagonal part of the Anderson model is just our integrable Hamiltonian. And what we have now is this Hamiltonian. Mu determines the site of our strange lattice, and perturbation determines the hopping between the sites. And as I told, what we need to have something close to the Anderson model is that hops, in some sense, are local, and we can distinguish between near and far. Okay, now let me give, how much time do I have? Okay, so very quickly, if I have Anderson model, I have, as I told, one particle, and it hops all over the lattice. What happens if I have n particles? Then, before I turn on the interaction, we will have n conservation laws, because each of our particles occupies certain one particle state. This state I will call alpha, and many-body state will be determined by the set of the occupation numbers. So if I'm dealing with fermions, some sites are occupied by one particle, some are empty. If I'm dealing with bosons, then occupation number can be any integer. And as I told, this set of occupation numbers determines the eigenstate of many-body system. And it is integrable just because we managed to write it in this diagonal form. And then if you will turn on the interaction and perturb your system, then what will happen is that two particles in different language can collide, and from two original state, they can go to two final states. And this is what I wrote here. So two states, alpha and beta, were occupied, but now will be empty. And two states, gamma and delta, were empty, but now will be occupied. And these are two different sides of this lattice that are connected by this perturbation. And this can be called connected bonded sides or nearest neighbors, what you want. And you can discuss it in terms of the Anderson localization. Now, this is another example which is also quite important. It's, if you want, a generalized Ising model in the presence of the perpendicular field. So we have this second term, which is Ising interaction. First term is parallel field along z direction, which makes maybe each Ising spin give it different energies. And what we turn on is terms that are connected with the perpendicular field. And here you have sigma x. And since sigma x and sigma z don't commute with each other, this, I think, this last term violates the integrability, which is, of course, due to the fact that if you don't have perpendicular field, your Hamiltonian commutes with each individual spin. And what we get again Anderson model, because sigma x is something that flips spin, and if we will consider this this system in the space of the integrals of motion of our integrable model, then each of these side is so-called bitstring. It's a set of numbers, let's say plus and minus 1, and that's why these sides determine some n-dimensional hypercube. N is total number of spins, and what the last term does, it provides hopping from one side to its one of its neighbors. And we get Anderson model, but instead of Anderson model with finite number of dimensions and infinite linear size, we get Anderson model with linear size of the system 1, but number of dimensions equal to going to infinity. But you can see that already 9 has enough complication in its topology to have interesting localization problem. So what I want to conclude is that the many-body localization, actually, from the point of view of statistical physics, is basically a statement that you cannot use anything that you learned from the statistical physics, because equipartition postulate is not valid. You basically put your particles in certain localized state, and it will stay there forever. No equilibrium, and no entropy production. And basically, this is different situation which should be analyzed in a different way. Okay, now just 3 minutes to discuss the most hot part of this story, which is about ergodicity. So first of all, what can we call ergodicity for quantum system? Remember, what Boltzmann introduced is this idea of ergodicity when averaging over time and space is equivalent to each other. And this was hypothesis. And for quantum system, what we propose is to discuss equivalence of the spatial average for a given realization of randomness and ensemble average. And basically, what we know is that what we can discuss, just one of the possible approaches is to consider what we in condensed matter physics call moments of the inverse participation ratio, and in mathematics are called renew entropies. And this is basically you take your particular wave function in a particular realization of disorder and calculate its absolute value to the power 2q, and for q equal 1, of course, you get 1 because we're dealing with normalized wave function. But for q's bigger than 1, what we will get something that is decreasing with the system size, and this decrease can be characterized by certain power tau, so that this tau 1 equals to 0. And if your system is ergodic, so if you have about n sites where wave function is about 1 over n wave function squared, then you can calculate that tau q will be q minus 1. And this is characteristic of the system completely spread over the allowed space. And if states are localized, of course, this moment of the participation ratio will not depend on q, because wave function is of order 1 at a number of sites of order 1, and what we will get is tau q equal to 0. And the statement is that there can be so-called multifractal or fractal states where this exponent is between 0 and q minus 1, and if you will normalize it by q minus 1, it is between 0 and 1. So this dq are called fractal dimensions, and you can study fractal dimensions of your wave functions. And for ordinary Anderson model, which I'm accelerating now, we have one Anderson transition, and we have for weak disorder extended states, for strong disorder localized states, and there is critical region where critical states are known to be multifractal, while as soon as you get out of the critical region, your states become either extended or localized. So you have one transition, and the point is that for many-body localization, it's at least not obvious, and we believe that there can be two transitions, one from localized to extended but not ergodic, and second from non-ergodic to ergodic. And in general, these two transitions, of course, can be close to each other or exactly at what point, but maybe not. And yeah, and yeah, yeah, and I actually finished. So these are further extensions of the field. We still have to understand better behavior of real many-body problems, and there is a separate branch of this activity which is about travel of one particle on certain graphs, like random regular graph, or all kind of examples, which maybe we will hear in this conference. And also what I have not even touched is actually dynamical properties of quantum systems. Thank you very much.
Okay, thank you, Boris, for this very nice lecture. We have very little time, but if there are some questions, please raise your hand. There's a question, please. Arun?
Thank you. Yeah, so I have a question. I mean, if I understood you correctly, you were saying that near integrable systems are in a sense MBL. Would that be correct characterization? I mean, you have an integrable system, and then you perturb it, and then you have the KAM theorem, and in the quantum context, you have some integrals or motion. I mean, quantum numbers that are conserved, and then you have a localization, which is you were making connections of that to MBL. Now my question is, some of the canonical models like Heisenberg with a disordered field, the Heisenberg is an integrable model, and if you perturb it with a little bit of noise, it actually goes into the ergodic phase rather than into the MBL. You need sufficient noise to actually destroy the ergodicity and go into localization. So it looks like it is a non-KAM system of some kind where, it's actually integrable, and then near integrable, you're actually going into a fully ergodic phase. Even the transverse field Ising model is like that. So it's an integrable model. You add a longitudinal field, you're going immediately into actually a chaotic or ergodic phase. Can you just comment on that, or what?
Okay, I either haven't understood you correctly or I strongly disagree. Because when you speak about integrable system and it's in violation of integrability, then you don't need disorder. The point is that states of integrable system are localized in quantum numbers of this integrable system. And if you violate the integrability a little bit, you are not going immediately to ergodic system. This is something that many people believe in, but I don't see any reason for that. So the statement is that unless you have some special case where every state of the integrable system by this perturbation is connected with every other state strongly, then you might have this transition going as soon as you turn on the violation of ergodicity, of integrability. But normally you need finite violation in order to go to ergodicity, like you need finite strengths of the perturbation in order to get out of KAM regime. And in quantum mechanics, localization is much stronger than in classical. And because of that, you need much more efforts in order to destroy integrability. But this localization, again, is not localization in real space. So, for example, if you add disorder, you first can get into the, I don't have a picture with me like right now, but I can show you
yeah, it's actually
later.
Fox space,
yeah.
So it goes.
That you can go to ergodic regime and then back to localized, but in different space.
Mm. Okay, I think we have a nice lunch discussion for you too, and maybe for others. I think we have to move on, so let's thank Boris Altshuler again for his lecture. Thank you, Boris.